Welcome to the next session of Subject Engineering Maths. We were discussing chapter 4 complex variables, and we were in the middle of discussion Cauchy residue theorem examples. Let us discuss one more example on Cauchy residue theorem. Suppose I want to find integral z square plus 1 by z minus 1 into z minus 2 into z minus 4 dz over the contour mod z equal to 3. Now this is a simple extension of previous example. In the previous example we don't have z minus 4. The result we got is 6 pi I. But here extra we have z minus 4. So what is my function? F of z is total function. This is z square plus 1 divided by z minus 1 into z minus 2 into z minus 4. So 1 comma 2 comma 4 are singular points of 1 comma 2 comma 4 are singular points of f of z, but 1 and 2 belong to this circle. They lie inside the circle, but 4 does not belong to this circle. Therefore here 1 comma 2 lie inside the contour mod z equal to 3, but the singular point 4 lies outside the contour. So in that case, how to get this value is by residue theorem. This is again 2 pi I times residue at 1 plus residue at 2 only, because 4 does not belong to this circle, so you need not find residue of this function at the 4. So therefore this result is again same as 2 pi I into residue of f of z at 1 plus residue of f of z at 2. But don't expect same answer as previous. Previously z minus 4 is not there in f of z. So you are getting 6 pi I. But here z minus 4 is there. The result will be same. I mean the formula will be same, but the result will be different. Okay. Because f of z is this. So let us find residue at 1. The residue of the function at 1 is, 1 is a simple pole. So this by calculation of limits, limit z tends to 1, z square plus 1 divided by z minus 2 into z minus 4. Now replace z by 1. This becomes 2 by 1 minus 2 minus 1 into 1 minus 4, or this is minus 3. So therefore the residue at the first singular point is 2 by 3. Next let us calculate residue of same function at the second singular point, that is 2. Here 2 is again a simple pole. So this is limit z tends to 2, z minus 2. Of course z minus 2 will be cancelled with this. So I don't write. This is z square plus 1 by remaining part z minus 1 into z minus 4. Now replace z by 2. This gives 5 divided by 2 minus 1 1, 2 minus 4 minus 2. So this is minus 5 by 2. Therefore this contour integral will be equal to 2 pi I into one residue is 2 by 3, second residue is minus 5 by 2. So this is 2 pi I into LCM of 3 and 2 6. So 2 2 is 4, 4 minus 15. So therefore this is 2 pi I into minus 11 by 6. So minus 11 pi I divided by 3. Minus 11 pi I by 3. So therefore in this way you will get the contour integral like this. Even if I have z minus 6. So 6 is a member outside the circle. Formula will be same, but the result will be different. Okay. So this is most effective. Work out this example. Let's start classroom workbook based on residue theorem. So let us start from question number 51. Classroom workbook question number 51. Let C be the circle given by z equal to 4 times e power I theta, where theta varies from 0 to 2 pi. It is a circle. Then the value of integral e power z by z square minus 2z dz over C. So this contour integral you need to find out. Here z is a circle. I mean C is a circle defined by z equal to 4 times e power I theta. So here z equal to 4 times e power I theta. So mod z equal to modulus of 4 times e power I theta. This is modulus of z1 times z2. So mod 4 into modulus of e power I theta. This is 4 because e power I theta is cos theta plus I sin theta. Its modulus is square root of cos squared theta plus sin squared theta. It is 1. So mod z is 4. Therefore, this circle C is a circle mod z equal to 4. Now this integral is integral e power z divided by denominator can be written as z into z minus 2 dz over mod z equal to 4. Now what is my f of z? Total function is f of z. F of z is e power z by z into z minus 2. So 0 is a singular point, 2 is a singular point of overall function. Both belong to this circle. So 0 comma 2 lie inside the circle mod z equal to 4. Therefore, this will be equal to 2 pi I times residue of this function at 0 plus residue of this function at 2. Therefore, let us find residue of f of z at 0. 0 is a simple pole. So, this will be equal to limit z tends to 0 e power z divided by z minus 2. Replace z by 0, we get minus 1 by 2. Now residue of this function at the second pole, that is 2. So this is given by limit z tends to 2. Anyhow, this z minus 2 will be cancelled. I am not writing this e power z by z. So this is e power e square by 2. So the first residue is minus 1 by 2, second residue is e square by 2. Therefore, this contour integral e power z by z into z minus 2 dz over c equal to 2 pi I into the first residue is minus 1 by 2, the second residue is e square by 2. So therefore 2 will be cancelled. This is pi I into e square minus 1. Pi I times e square minus 1. So option D is right answer. So simple calculation, find the residues, add the residues and multiply with 2 pi I. So the answer is D. Next we move to question number 52. An integral I over a counterclockwise circle given by I equal to integral z square minus 1 divided by z square plus 1 into e power z dz over a circle C. If C is defined as mod z equal to 3, then what is the value of I? So this contour integral you need to find integral z square minus 1 by z square plus 1 into e power z dz over mod z is 3. The direction of the contour is counterclockwise. Now what is my f of z? Total function is to be taken as f of z. So f of z is z square minus 1 by z square plus 1 into e power z. Now here the denominator is z square plus 1. So actually z square plus 1 can be written as z minus I into z plus I. So this is analytic at all points. This is analytic at all points except at I and minus I. So the singular points of this function are roots of denominator expression I and minus I. Both I and minus I belong to this circle. So I comma minus I lie inside this circle mod z equal to 3. Therefore, we need to find the residue of overall function at two different singular points I and minus I. Of course, both are simple poles. Now let us calculate residue of the function f of z at pole I. This is simple pole. So this is limit z tends to I. Anyhow, this z minus I will be cancelled. So this is z square minus 1 into e power z divided by z plus I. So replace z by I square is minus 1. So minus 2 into this is e power I divided by this is 2i. So therefore minus e power I divided by I. So the residue of this function at the pole I is minus e power I by I. So let us find residue of same function at the second pole, residue of f of z at minus I. So this is the limit z tends to minus I. This will be cancelled out, z plus I. Then this becomes z square minus 1 by z minus I into e power z. So replace z by minus I square. So this is minus 2 by minus 2i into e power minus I. So this is e power minus I divided by I. One residue is minus e power I by I. Second residue is e power minus I by I. Therefore this integral I is 2 pi I into residue of f of z at I plus residue of f of z at second singular point. This is minus I. So therefore this is 2 pi I into residue at I is minus e power I by I. This is plus e power minus I by I. But the answer is given in terms of sine function. This is in the form of e power I theta. Even it is in the form e power I theta. So what is e power I theta? E power I theta is cos theta plus I sin theta. So here theta is 1. Therefore this can be simplified like this, 2 pi I. Anyhow this I will be cancelled, 2 pi into this is e power minus I minus e power I. So this is 2 pi into this is cos of theta is minus 1. Cos of minus 1 plus I into sin of minus 1 minus e power I theta. Here theta is 1. This is cos 1 plus I sin 1. Anyhow cos is an even function. So cos of minus 1 is same as cos 1. So therefore this is 2 pi into sin is an odd function. So this is minus I sin 1 minus I sin 1. Therefore this is minus 4 pi I sin 1. So the final value is minus 4 pi I sin 1. What we have done is we have applied the formula e power I theta is cos theta plus I sin theta. Here theta is 1. Here theta is minus 1. So few terms have been cancelled. Cos terms have been cancelled. So sin is odd function. Sin of minus 1 is minus sin 1. So finally it gives minus 4 pi I sin 1. So option D is right answer. Integral 3z minus 5 divided by z minus 1 into z minus 2 dz along a closed path C is equal to 4 pi I. Interestingly, the value of the contour is directly given. Contour integral value is directly given. So we need to find the correct path of C. So here two z naughts are there, 1 and 2. So this integral is equal to integral 3z minus 5 by z minus 1 into z minus 2 dz over C is equal to 4 pi I. The correct path of C is, options are very different. Very interesting question this is. Now let us go through options. Let me write out options first. So the correct path of C, that means the path of C is given like this. This is contour C. So 1 inside, 2 inside. Second option, again coordinate system, x-axis and y-axis. So the contour C is moving in anti-clockwise direction, but 1 inside and 2 outside. And option C, 1 outside, this is contour C, 1 outside but 2 inside, x-axis, y-axis. And option D, this is x-axis and y-axis, contour C along anti-clockwise, 1 outside, 2 outside. So till now we have handled many questions when C is given directly. But in this case, the contour integral value is directly given as 4 pi I. They were asking the correct path of C. So what are the singular points of total function 1 and 2? So here my f of z is 3z minus 5 divided by z minus 1 into z minus 2. So 1 and 2 are singular points of this function. 1, 2 are singular points of f of z. Now look at option number D. Here one lies outside the circle, 2 lies outside the circle. When both lie outside the circle, the integral becomes 0, but this is non-zero expression. So option D is wrong. So let us find residue at 1 at first. So residue of f of z at 1. 1 is a simple pole. So this gives limit z tends to 1, z minus 1 into f of z. I am applying case 1 of residue procedure. So therefore this is limit z tends to 1. So z minus will be cancelled. We get 3z minus 5 divided by z minus 2. So this expression becomes minus 2 by minus 1. This is 2. So when you calculate residue at 1, we were getting 2. But according to Cauchy's integral formula, this value, this integral, for example, you call it as I. So this integral I must be equal to 2 pi I into residue. So this is basically residue of f of z at 1 plus residue of f of z at 2. If both belong to this circle, actually this may not be right, I am writing just for formality. But only this residue of f of z at 2 is giving 2. 2 times 2 pi I is 4 pi I. That means you need not calculate residue at 2. It is not required. So don't calculate residue at 2. So 2 pi I times 2, it is directly 4 pi I. That means I am not calculating residue of this function at 2. What does it mean? 2 lies outside the circle, but 1 lies inside the circle. So 1 inside, 2 lies outside the circle. The correct path of B is this. Note down this point. Integral e power z by z square minus 3z plus 2 dz, where the contour C is the circle, that is mod z equal to 3 by 2. So we need to find this integral. Now what is my f of z? Overall function is f of z. E power z whole divided by z square minus 3z plus 2. So therefore this is e power z by, the denominator is z minus 1 into z minus 2. So its singular points are 1 and 2. Both belong to, of course 2 does not belong to this circle. So here 1, 2 are singular points. 1, 2 are singular points of f of z. 1 lies inside the circle, inside C, but 2 lies outside the circle. 2 lies outside the circle. This is my contour C. So mod 1 is 1 less than 3 by 2. Mod 2 is 2 greater than 3 by 2. So only 1 inside, 1 outside. So therefore I will find residue only at 1. So this formula is, actually this integral is 2 pi I into residue of f of z at 1 only. Now let us calculate residue at 1. Residue of f of z at 1 is a simple pole. So this will be limit z tends to 1, z minus 1 into f of z. I have applied case 1 of residue. Case 1 of residue. So therefore this is limit z tends to 1. This is z minus 1 into, what is f of z? E power z by z minus 1 into z minus 2. This and this will be cancelled. So this is e power 1 by 1 minus 2. So this is minus e. So therefore this integral, if I call it as I, then this contour integral I will be equal to 2 pi I into this minus e. So therefore this is minus 2 pi I e. Minus 2 pi I e. So option C is right answer. See here we got two singular points 1 and 2. but only 1 belongs to this circle, but 2 does not belong to this circle. So you need not find residue of total function at 2. So this integral is 2 pi I times residue f of z, residue of f of z only at 1. Here 1 is a simple pole. Apply case 1. My answer is minus e residue. So multiply with 2 pi I. It becomes minus 2 pi I into e. Option C is right answer. 5. The value of the integral 2z plus 5 divided by z minus 1 by 2 into z square minus 4z plus 5 dz over the contour mod z equal to 1 taken in the anti-clock direction would be. Options are given. See, when you simplify, actually when you find the roots of denominator, you will get 3 z naughts. One z naught is 1 by 2. You need to get 2 z naughts from this. So based on how many z naughts belong to that circle, I need to find residues of those many points. Okay. Now here one z naught is 1 by 2. 1 by 2 lies inside this. Lies inside mod z equal to 1. Therefore, obviously, I need to find the residue of overall function at 1 by 2. That is very clear. Now, let us factorize this. Z square minus 4z plus 5. This is equal to z square minus 4z plus 4 plus 1. Now, this is what z minus 2 whole square plus 1. The factorization of z square plus 1 is z minus I into z plus I. Now let us find the factorization of z minus 2 whole square plus 1. This is factorization of z square plus 1. Now in place of z we have z minus 2. Let us apply same. So this is z minus 2 minus I into z minus 2 plus I. So here one z naught, this is nothing but z minus of I plus 2. Z minus of I plus 2. And this is z minus of minus I. This is z minus of I minus 2. I plus 2. This is plus only. And this is z minus 2 minus I, z minus 2 plus I. This is z minus of I plus 2. Yes. This is z minus of I plus 2. So one z naught is I plus 2. Second z naught is minus I minus 2. When you find the modulus of this, actually this is the complex conjugate of this. Let us find the modulus of I plus 2. This is square root of 1 square plus 2 square. This is square root of 5. It is greater than 1. Similarly, modulus of minus I minus 2. This is again root 5. This is greater than 1. So these 2 points lie outside this circle. So therefore I plus 1 only 1 by 2 lies inside, but I plus 2 comma minus I minus 2 lie outside the circle mod z equal to 1 by 2. The circle is 1. Mod z is 1. Therefore this integral we can call it as f of z. So what is my function? F of z is 2z plus 5 divided by z minus 1 by 2 into z square minus 4z plus 5. So therefore the residue, I need to find residue of this function only at this 1 by 2. Because the z naughts coming from this expression lie outside the circle. So I don't find the residue of this function at the remaining 2 z naughts. I will find residue of this function only at 1 by 2. So residue of f of z at 1 by 2 equal to limit z tends to 1 by 2. This z minus 1 by 2 term will be cancelled. So I am not going to write this. Limit z tends to 1 by 2. 2z plus 5 by z square minus 4z plus 5. So replace z by 1 by 2. So this becomes 2 into 1 by 2. This is 1 plus 1. So this is 6 divided by 1 by 2 whole square. 1 by 4 minus 4 into 1 by 2, 2 plus 5. So 2 by, the LCM is 4, this is 1 minus 8 plus 20. So therefore this expression is 2 by, this is, you can write like this, 6 into 4, 24 divided by 21 minus 8, this is 13. So the residue is 24 by 13. If I assume that this integral is I, then my integral is 2 pi I into this residue. This is 24 by 13. So therefore this is 48 pi I divided by 13. So the final value is 48 pi I by 13. So option B is right answer.